You're listening to Wurth Electronics What's Up radio podcast, where each week we are seeing what's up in the world of electronics and PCB design. We'll be checking in with leading industry experts and Wurth Electronic technical specialists who are going to shine a light on our topics, such as energy harvesting, wireless power transfer, EMI issues, and so much more. Tune in to get technical design tips and applications during your commute, at your desk, or wherever you might be with Wurth Electronics What's Up podcast. Well, it is the season. The stress of the holidays is enough for any one person, and you shouldn't have to feel that pressure on your applications too. Today's podcast is all about pressure sensors. Now, recently, pressure sensors have shrunk in footprint, transitions to digital, and they've become more energy efficient. Many different types of differential pressure sensors are required in many industrial applications. Those are the ones we're going to focus on today. And the choice of the pressure sensor depends on the end application. Today, we're showing examples of applications with differential pressure sensors, and we're going to explain main key features and characteristics. We'll also give a comprehensive overview of MEMS-based pressure sensing technology, and we'll finish off with a discussion of the differences between analog and digital sensors.
We will start with what is pressure or what kind of pressures are there. Then we will go ahead with MEMS-based pressure sensors and look into which types of pressure sensors are available and how the pressure sensors have evolved throughout the years to show the scale of integration in the pressure sensors, and have a look at some of the applications, and also shed a light on what type of pressure sensors to use, for example, pressure or flow sensor, or even to use a digital sensor or an analog sensor. And in the end, I would like to show some of the pressure sensors from our Wurth Electronic portfolio and focus on also the individualization service that we provide. So what is pressure? So basically, pressure is the force applied per unit area, and we all are aware about the atmospheric pressure, which is due to the atmosphere around the earth. So basically, when you are near to the surface of the earth, you have a higher pressure due to more atmosphere, and if you go higher up the altitude, then you will have less pressure. So depending on where you are, what time of the year it is, or what time of the day or weather, the atmospheric pressure will be always changing. When we talk about atmospheric pressure, this is always measured with respect to the vacuum, which is zero. So the atmospheric pressure is an absolute pressure. So absolute pressure is always positive because it is always referenced to absolute vacuum or zero referenced. On the other hand, if we take reference as atmospheric pressure instead of vacuum, and then measure the pressure, we can either have a positive pressure or a negative pressure, and this is called a gauge pressure. And the last is the differential pressure, which is nothing but the difference between any two pressure. So it can be either positive, negative, or anything. For in principle, an absolute pressure can also be called the differential pressure theoretically. Moving ahead, we talk about MEMS-based pressure sensors. So here there are different kind of MEMS technology available in pressure sensors, namely piezoresistive technology or capacitive technology. For differential pressure sensors, piezoresistive technology is more popular, so we are going to focus on the piezoresistive technology. So this is based on the piezoresistivity, where the resistivity of the material changes when the material is under stress or any force or pressure. So basically what we do here is that we have a silicon substrate, and which is etched from the backside, and with an chemical etch stop layer, we can stop the etching so that we have a very thin silicon membrane. On the top side, if you see, then we have a thin membrane which is suspended in the air, and on the edges we dope the piezoresistors. So we have the piezoresistor which are doped on the suspended silicon membrane. And whenever there is some force or pressure applied on top of the membrane, which is very thin, so very small deviation can also be can also cause the deviation in the membrane. And that's why the piezo resistivity of the piezo resistor will change, and this will be the material will be under maybe compression or tension, depending on what type of or what and what direction the pressure has been applied. So these piezoresistors are electronically connected in a Wheaton bridge, and they are supplied with voltage. And whenever there is a pressure from the top side, because of this pressure or force, the resistance of the piezoresistor will change, and then bridge will be in imbalance, and we will have some voltage drop across the Wheaton bridge. This voltage drop in the end is directly proportional to the what pressure is being applied on top of the membrane. So we will have some millivolt output. It is important to notice here that this output is purely analog for sure, and this is also not calibrated or also not compensated. Some benefits of this piezoresistive technology is that the sensors or the output characteristic is highly linear because of the resistors, and it is easy to produce, and there are no complex structure inside, so it is also not so costly in terms of production. Disadvantage is that the piezo-resistive technology is very sensitive to the temperature changes. So if the temperature changes, then the output may also change. Now let's go back to the previous slide where we showed different pressures, and now we can apply the piezoresistive technology and have all three different kinds of sensor. So for example, here we have in gray the piezoresistive silicon part, which is sealed inside a vacuum so that we have a sealed vacuum during production. And then we encapsulate it, and then through one outlet port, the ambient pressure can get inside. So the pressure measurement is done always against the sealed vacuum, so we have an absolute pressure sensor. For the gauge pressure sensors, not we have a hole on one side of the sensor, and the other side of the sensor is where you apply the pressure. So basically, in the end, we are measuring the pressure against the atmospheric pressure, and we have a gauge sensor. Not very far from the construction of a gauge sensor is the differential pressure sensor, where you have possibility to connect two different pipes with two different ports, and you can measure the difference between port P1 and port P2, so that you have in the end a differential pressure sensor. Next, in my opinion, is one of the important slides to understand what scale of integration is doing in terms of the pressure sensor. For example, what type of pressure sensors are available today in the market. The most basic ones are just the MEMS measurement cell, what we saw, the silicon, only the bare silicon die, where you have the piezoresistor in Wheaton bridge and some measurement points to take the output. So this is the purely MEMS cell, which is purely analog. It is also not calibrated or also not temperature compensated. And this is available as a bare die or a package die, which you can use in your end applications. And also then you need to take care if you want to have it connected to some microcontroller, then you have to take care of designing an amplifier and also put it to and put an ADC so that you have a digital signal. So these things then at the end application needs to take care. Another type is the amplified sensor. So now with the measurement MEMS cell, we have the amplifier which amplifies the output signal, and also in some cases we have passively compensation, which with the laser trimmed resistors, where you do the temperature compensation of the output with fixed temperature with the laser trimmed resistors. So usually these are both calibrated and compensated, but in the applications where a dynamic temperature is being used, or there is a big difference between temperature in the application, then this sensor might not have accurate output at all of the temperature, because the passively compensation has a very narrow temperature window. And the third one is the integrated sensors. And now we have for all the calibration and compensation a dedicated IC on the board, which has also a signal processor and also memory. So whenever we get a signal from the MEMS die, it is then amplified, digitized with an ADC, and the values are stored in the memory. And during the calibration process in the production, the calibration coefficients are also stored, so that during the application or when you fire up the sensor, these coefficients are loaded and you get always the digital or fully calibrated output. And there are also digital and analog interface inside the IC, so that you can directly connect them to microcontroller or host controller. So from a basic sensing cell to an integrated sensor, there are different types of sensors available, and this is the which one to use depends vastly on what type of application you are aiming for. When we talk about applications, there are many types of applications where the pressure sensors are being used. Some of them are, for example, smart buildings, where in HVAC systems or in white goods, uh, washing machines, dishwashers, or coffee machines, or even the smart vacuum robots, where the pressure sensors are being employed in the HVAC systems. Also, multiple sensors are used, or more than one sensors are used, and they are all connected to in a bus and connected to one microcontroller. Even in health monitoring, for example, blood pressure monitoring, you have a differential pressure sensor employed. So these applications always demand, for example, low power consumption. When there are applications, for example, blood pressure monitoring, they are battery operated. So the sensor should have a very low power consumption. Also, many times they are employed in higher volume for white goods or HVAC systems, and multiple sensors are connected with one another or on a single bus. In the industrial applications or the smart factory, for pump monitoring or pneumatic controls or robotic arm controls, the pressure sensors are employed. Or even an interesting application is for the room pressure monitoring, for example, for the operation theaters, or even for clean rooms, where the rooms should have a higher pressure with respect to the corridor pressure, so that the bacteria or contaminants cannot enter the room and the environment inside is always clean. For these purposes, the pressure sensors are used, and these kind of applications require a real-time monitoring, so that you can always have a look at what is the status of the system. They should have a precise measurement, accurate measurement, and also the response they should respond to they should respond quickly to pressure changes. Let's have a look at the HVAC application in details and how the HVAC industry has evolved throughout the years, because of the climate change, now more and more HVAC systems are being employed, and they are already being made better and better throughout the years. So initially in these systems, analog pressure switches were used. Now we are using the pressure sensors, with which you can still, for example, control your smart thermostat and have a perfect air quality or air temperature inside. And now more and more connected sensor networks are being employed. So there are more than one sensors inside, for example, temperature sensor, humidity sensor, gas sensor, and also pressure sensors are implemented. And these all sensors are connected to a host controller, and they should give a digital output as well. So the systems are getting low maintenance, smart, energy efficient, and also more and more automated. And this also requires in the end to have the sensors compatible with these kind of systems. So the sensors with long-term stability or lower power consumption, or IoT ready, or ready to be connected to a wireless system easily, or plug and play solution for the sensors are more suitable for these kind of applications. In the HVAC, another important monitoring is the filter monitoring. Because of current corona situation, the indoor air quality is now more important than ever, because we now spend more than 70% of our lives indoors, and indoor air has more pollutants than the outside air, and we breathe the same air while being indoors. So every HVAC system has an filter so that you get a clean air inside, and with time the filter gets dirty, and it is very important that you change the filter at the right time. For example, if you change the filter too late, then your filter is too clogged and you might not have enough airflow, and your cooling or heating efficiency is not enough. This will also lead to higher energy consumption and higher costs, and in the end, because the filter is not fully compatible or fully functional, you will have a poor indoor air quality. On the other hand, if you change the filter too early, then you have increased material cost and waste of materials, which is not environmental friendly. So it is very important to change or clean the filter at the right time. So a solution would be to use a smart filter monitoring system where you have a differential pressure sensor connected both ports on either side of the filter, and then whenever filter is clogged, there is a very high pressure difference between the high pressure side and low pressure side. So here at P1 the pressure starts to build up, and after a certain threshold the sensor will alert the microcontroller or the system that it's time to change a filter. Some more applications are for flow control and regulations, where for ventilator control or fan control, you can also use the differential pressure sensor, or also, as we mentioned, for the constant air pressure control, you can use the differential pressure sensor in a gauge configuration where you can have a constant pressure built up inside the vent. For the flow measurement, many times a pressure sensor or even the flow sensor is being used. So this also depends on your application, what kind of sensor you need to employ, because pressure sensor and flow sensor in the end, they are completely different. They work on completely different technologies. The pressure sensor we saw here with the membrane. On the other hand, the flow sensors have a small heater, and the air is passing through the heated element so that air gets heated up, and then because of the heat dispersion between the vent or between the inside the sensor, there is a different air temperatures, and this can be measured through electrically what is the flow of the system is. If we compare the flow sensor and pressure sensors, then they are completely different. For example, flow sensor is usually calibrated at with certain gases. So in the application where other gases needs to be used, they need to be again calibrated. This is not the case for the pressure sensors. Also, because there is a heater, so the heater heats up the air and it consumes a small amount of energy, and also heating of the air also takes a little time. So basically the flow sensors are usually have a slower response time and also consumes a bit more power compared to the MEMS based pressure sensors. But on the other hand, these flow sensors are suitable for ultra low pressure measurement, because they have a very good zero pressure or zero flow stability, because there is no moving parts inside basically, or the system is not under any stress. But the flow sensors are not very much resistant to contamination, because the air is flowing directly through the sensor. So whenever the sensor gets clogged, you do not get a correct flow or pressure output, which is not the case in the MEMS based pressure sensors, because whenever there is some contamination, there will be a delayed frequency response because of the contamination, or you might have some offset due to the contamination, which you can get rid with the help of the host controller, or write some code so that you get rid of this offset. Then we also can compare different output based on sensors. Usually the integrated sensor, pressure sensor usually have analog or digital output, and it is important to see what kind of application I'm going to use these sensors for, and based on that I can choose the output, whether I need a digital output or an analog output. For example, the analog sensors have very high accuracy, but digital sensors have a higher resolution based on the type of ADC you use. The digital sensors can have a very low current consumption overall, because the sensors have inbuilt interrupt functionality sometimes, where you say the host controller is put to sleep and only the sensor needs to be active, and the controller doesn't have to always ask for the new pressure data. Also, digital sensors usually have the temperature sensors on chip, so you can also get some temperature data. So at the end, you might get one less material on your BOM list and use the temperature information from the digital sensor itself. But on the other hand, if some application require some variable current output or variable voltage output, then purely analog sensors needs to be used. And for the application which require wireless connectivity or cloud connectivity, where your sensors directly send the data to a wireless module, then it's better to have a digital output, so that you have a kind of a plug and play system where it's very easy to connect the sensor to the wireless module and have the access of the data remotely. Let's now have a look at some of the pressure sensors what we have in our portfolio. So we have as a standard differential pressure sensor, the low, medium, and high pressure range, which starts from 0 0., plus or minus 1 kilopascal to 1500 kilopascal. These sensors are 5 volt, works at 5 volts, and they have 15 bits of ADC resolution. And the sensors are I2C and analog. So digital I2C and analog output, both of them are available in parallel. So you can either choose to read out the data with the digital interface, or also have an analog output. So these are the fixed configuration. So in this configuration, so the sensor is perfectly suitable for multiple sensor networks, where you need more than one sensors on the same bus, or even in the battery-driven applications, or for real-time monitoring. With the digital interface, you get fast data transfer, or even for wireless data transmission, the sensors is suitable. But in case these fixed configurations are not enough for your application, then we also provide the individualized differential pressure sensors. For example, you might have a horizontal nozzles instead of the straight nozzles, so that it's easier to connect the tubes to the sensors, or even different pressure measurement range based on your applications, or even operating voltage can be reduced to 3.3 volt for battery operated devices, or even have a lower resolution, so that you can have a faster response time, or additional SPI digital interface, or even have an inbuilt alarm, so that the pressure, whenever the pressure is high or low below a certain threshold, the sensor alerts the microcontroller. So this could be a very good example for power saving applications. Let's have a look at the cross section of the differential pressure sensor. How does it look? We have in the standard product, we have two ports on the top side. The port 1 connects directly to the top side of the MEMS element, and the MEMS element is directly placed on a ceramic, so that it provides a better thermal and mechanical stability, so that it has a better offset performance. And the other side of the MEMS element is directly connected through a hole in via an embedded pneumatic channel to the other side of the port here, and the MEMS and ASICs are then bonded to the PCB. So in the end, we have a leadless SMD package, so you can also do hand soldering if required for prototyping. The block diagram, as we saw that we have a MEMS cell here, so this is the sensing element, and then an ASIC connected to the MEM cell. So the ASIC includes the amplifier and also an on-chip temperature sensor. So these are then multiplexed, and through an ADC they are converted in the digital form and stored in the digital signal processor. And during the production, the calibration parameters are also stored inside the memory, so that each time you measure the pressure data, the calibration parameters are also loaded, and you get the digital output through the digital interface, which is fully calibrated. As mentioned, we also have an analog output in parallel. So the analog output is then going through one more step of digital to analog converter. So the digital output is again converted into an analog output through DAC, and then you get a fully calibrated and fully compensated analog output. So here what analog output we get is not a purely analog output, and this is fully calibrated output. In the end, we do also offer an all-inclusive evaluation boards, which makes the tube connections very easy for your prototyping. For example, for the standard products sensors, you can connect the tubes of a 2 millimeter diameter directly to the sensors. For the horizontal nozzle, the sensors the ports are barbed, so they give you better connection with the sensor. But with our evaluation board, you also get an adapter and O-rings for the sealing, which you can use for your prototyping, where you can use the standard 6 millimeter pipes to connect the sensor to. And this is very important in terms of mechanical stability, because the electrical joints for the sensor or the soldering joints are not made to withstand the mechanical stress that comes with the pipes connected. So when we use this adapter, there is less stress on the sensor, and also in terms of hazardous gases, when there is a danger of leakage, this provides an additional safety. The CAD file for the adapter is already available on our website, so maybe you can also use it for your applications, or maybe modify as well, depending on your requirements. That brings us to the end of our webinar, and in summary, I would like to show what our sensor offer. As mentioned, I2C or analog output and also inbuilt temperature sensors is also available. The sensors are based on piezoresistive, and they provide the digital calibrated and compensated data. So kind of plug and play applications where you can connect the sensor directly to a host controller and send the data to cloud very easily. We have no MOQs. There is also an evaluation board, as mentioned, available for your faster prototyping, and we have a software development kit available, so that you don't have to go through the whole programming process. You can just load the SDK from our website and use it on your controller.
Attached images are available in most podcast streaming networks. Visit Wurth Electronic online to find the entire line of sensors, including differential and absolute pressure, temperature, acceleration, and humidity sensors. This podcast was taken from an updated Wurth Electronic webinar. To view the materials and replay the webinar on demand, visit www.we-online.com/webinars or click the link attached in this podcast. You're listening to Wurth Electronics What's Up radio podcast, where each week we are seeing what's up in the world of electronics and PCB design. We'll be checking in with leading industry experts and Wurth Electronic technical specialists. We'll shine a light on our topics like energy harvesting, wireless power transfer, EMI issues, and so much more. Tune in to get technical design tips and applications during your commute, at your desk, or wherever you might be with Wurth Electronics What's Up podcast.